So as I just mentioned, next time, which is next Monday, we will have our first midterm of the semester, and my plan today is to go over what we did during the, so far in the lectures that we had so far. And but before that one, we can talk a little bit about how the exam will look like. So of course it will be on Canvas, as we said already a few times. So next Monday at 7:30 the exam will become available on Canvas. So you will see it on Canvas. Then basically you will look at it, you will solve the problems, and then you also have to submit it on Canvas. So that is supposed to be during our lecture time. So it will open at 7:30, and the assignment will close at 8:45. So you have 1 hour and 15 minutes to solve the problems, the questions, and submit your exam. You can decide to use, let's say, a tablet, if you have a tablet, some whatever you use, or if you, and then submit the PDF, make a PDF out of your whatever note software you use, or you can simply do with paper and pen, and then you can scan and submit the scan always in PDF of your solution. Yes. Well, it will be 1 hour and 15 minutes total. I think it will take less than 10 minutes to scan and submit. What I can do, instead of doing like 1 hour and 15 minutes, I guess we can extend a little bit, let's say to 1 hour and 20 minutes. So you have those extra 5 minutes to scan and submit. So instead of doing 8:45, we can do 8:50. Okay? So you have like a full 1 hour and 15 minutes to solve the problems, think about the questions and so on. Any other question about the format? Yes, it is on Monday. Other questions about the format of the midterm? So, other thing that I want to mention is that you are allowed to use the textbook and your notes. And you may need to search something on the internet. For example, you may need to search let's say the moment of inertia of a certain shape, or some material property, for example. So you are allowed to do that. Maybe some of this information are in the textbook as well, I'm not sure, but you can use the internet for this only. You cannot use like AI. To be honest, I tried to solve the problem with ChatGPT, and I saw some errors, honestly, something that I had to fix. So my suggestion is actually of not using, not even trying to use, because it can be misleading. And if I find some errors, in one of your solutions that I found on, ChatGPT, that will be a big red flag, and I may need to give like 0 to the exam. So again, my suggestion is not even trying, because it can be very misleading and can be a problem. But of course you can use your notes and the textbook and so on. Also, of course, you can collaborate with other people, either in this class or outside of the class. It's an individual test, and you should be able to solve the problems and answer the questions by yourself. Makes sense? So a question: do we also log into Zoom during the midterm? We are not gonna have the Zoom during that time, so so we don't log in into Zoom. Okay. Other questions? All right, so we talked about the format, we talked about what you are allowed to do and not allowed to do. We can talk a little bit about the content. So, as I mentioned, the exam covers whatever we did up to last week. So basically it will cover, let me see, I'm going to take my notes actually. It will cover up to the energy method to find the equation of motion and the natural frequency of a certain system. So of course now after this we will go over the topics that we covered so far. Also, I didn't finalize yet, but I have a pretty good idea of what I will include, and I will include a few multiple choice questions, and I will include a couple of problems. And again, the multiple choice questions and the problems can be about anything we did so far. So my suggestion is to go back. Of course, now again we are doing a little bit of review, but my suggestion is to go back to your notes and see all the problems that we did. Also look at the homework that we had so far. The next one is due this Friday. You already have the solution of the first two, number 1, number 2, they're already posted on Canvas, and then I will post the solution of the third one also Saturday, because the due date is Friday night. If you don't see the solution by Saturday, let's say before lunch, please send me a reminder email and I will post. It's already there. I just need to publish it. Unfortunately, I cannot set in advance. One day Canvas probably will do this. Will let me do this as well. Make sense? So again, couple of problems, and also 10 points will be given to neatness and organization. So please make sure that for the problems you include all the steps that you use to solve the problems, you clearly organize them, and also for the multiple choice questions you just mark one question. If you can write down which question and which answer, because you are not going to have the printout of the test like we do in class. So in your notes, in your solution, you can just write down which question and then which answer is the correct answer for you. Make sense? And then for the problem, of course, make sure that you go over all the needed steps. Yeah, that will be enough. Make sure that you give only one answer, because only one answer is the correct answer to the multiple choice questions. Other questions? No. If you are asked to plot something, it will be a qualitative schematic, and you can do that by hand. Very good question. I was thinking about mentioning this, but I forgot, so thank you for asking. Other questions? Not yet. you will know next Monday at 7:30. Other questions? Alright, I think at this point we can start our review. Maybe other questions will come up while we go through our review. Okay, so let's restart from the very beginning. So the very first thing that we looked at is a very simple vibrating system, which is a single degree of freedom system. To make it shorter, we can write SDOF. And in particular, we looked at a subcategory of single degree of freedom systems because we looked at undamped systems. That's right. Let me share screen. So again, the first type of system that we introduced are single degree of freedom systems, and in particular undamped systems, which means that these are systems that are typically made out of a certain spring and a certain mass. So we typically need to know the properties of the system in terms of elastic constant of the spring and mass of the block that is connected to the spring. If you remember, once we looked at this system, the very first thing that we did was to write the equation of motion. To write the equation of motion, we used the force method, which means we look at all the forces that were applied on this block. In this case, we look at the motion that occurs in the horizontal direction. So of course we look at the forces in the horizontal direction. The forces in the horizontal direction for this one are the force of the spring and the inertia force, which is basically the product between the mass and the acceleration. Once we write the equilibrium equation, we can simplify the equilibrium equation, and then we come up with this form of the equilibrium equation, where we have x double dot plus omega n square x equal to 0. So this is the standard form of the equilibrium equation, where we have second derivative of our function, we also have our function, and then we have this term here, which is the natural frequency of the system. In this case, if we want to find the natural frequency, of course we look at this term here, so we will have that omega n will be equal to the square root of k over m. And when we write the natural frequency in this form, it is expressed in radians per second. All right. Now that we have once that we have the equation of motion that describes how the system behaves, what we should do is to find a solution of the equation of motion that describes basically how our x, so the coordinate x, the displacement, changes with time. We start by looking at the general solution, which is the form of x of t equal to a sine of omega n t plus phi, where a is the amplitude and phi is the phase. Again, this is the general solution. We need to find the particular solution in order to find a particular solution, we need to introduce the concept of initial conditions, which means that we have to introduce initial position and initial velocity. And I don't know if you remember, but once we introduce the concept of initial position and initial velocity, that we can call x0 and v0, we can derive this function twice. So we plug the second derivative here, then we plug the function here, and then through a few steps we can determine again the value of these two constants, a and phi, through a few through algebraic steps. Once we go through these algebraic steps, what we obtain for amplitude and phase is the following. We have that the amplitude is equal to omega n squared x0 squared plus v0 squared divided by omega n, and then the numerator is with square root. For the phase, indicated with the Greek letter phi, we have the inverse of the tangent of x0 omega n divided by v0. From this equation, we can directly see that the system is undamped, it is also free, which means that we don't have external forces. This also means that if both the initial position and the initial velocity are 0, so if these two terms are equal to 0, it means that the amplitude is 0, which means that we don't have any motion for our mass in this case. Again, it is a free system, we don't have external forces, so in order to have motion we need either initial velocity, initial position, or both. Which means that if we have the mass here, we can apply a certain displacement in one direction or the other direction, and then we release the mass, and then the mass will start to move back and forth. Make sense? So, of course, now we have the particular solution of our equation of motion, so we can plug this quantity here and this quantity here, and assuming that we have values of elastic constant, mass, initial position, and initial velocity, we can plot finally our displacement as a function of time. Now I'm going to plot a qualitative diagram, because we don't a qualitative function, because we don't have numbers, but this is how it looks like. So here we have time, here we have x. This is a qualitative expression, a qualitative plot of the function. Makes sense? Of course, we don't have any element that will dissipate the energy basically in the system, which means that once we give the initial either position or velocity, the system starts to oscillate, and theoretically it will continue oscillate forever. By looking at this wave here, because this is nothing but a wave, we can define also the period that we typically indicate with uppercase T as 2 pi over omega n, and this is in seconds. And we can also define the frequency in another way, which is the inverse of the period, which means omega n over 2 pi, In this case, the units that we use is hertz. So in order to avoid confusion between this form of the frequency and this form of the frequency, we always refer to the units that we use. So the frequency that comes straight out of the equation of motion is in radians per second. When we introduce 2 pi, we basically convert this one in hertz. When we talked about single degree of freedom systems that are undamped, we also introduced another very simple and very common system, which is the pendulum. In this case, let's say the physics behind the problem is identical to the physics that we have here, which means that the type of equation that we use to describe this system is identical to the equation that we use to describe this system. So even in this case, the equation of motion looks like theta double dot plus g over L times theta equal to 0. And even in this case, the natural frequency will be given by the square root of this quantity here, the coefficient of the theta term. So omega n is equal to square root of g over L. Of course, the solution will be in the exact same form of the solution that we saw here, which means that we also need to find the initial conditions. In this case, the main difference is that here we talk about a rotating system, so we use the variable theta to describe what's going on. Here we have a translational system, so we use x to describe what's going on. So here the initial conditions are in terms of x0 and v0, so initial position, initial velocity. In this case we talk about initial conditions in terms of rotation and angular velocity. So we can have an initial rotation and initial angular velocity. But once we basically replace all the quantities here like x0 and v0 with theta 0 and theta dot 0, the mathematical form is identical. Questions? No questions? Yeah, in this case, yes, it's just a matter of using different symbols. Instead of using x, here you use theta, but the process will be the exact same. So after talking about single degree of freedom systems, undamped and free, we moved to another type. So we talked about still single degree of freedom systems, but in the second round we introduced the damping. So in this case we talk about damped systems, still free. so far we didn't introduce any external force to our system, so it's still a free system. If we want to do a schematic of how this would look like, if we consider the we consider our block here, we still have the spring with a certain constant k, we still have the mass. In this case we have an extra element, which is the dashpot. Exactly like we did for the undamped system, we took our body, we looked at all the forces that are involved, that are applied actually to this body. Even in this case we only have motion in the horizontal direction, so we look at the forces in the horizontal direction. In this case the forces in the horizontal direction are the force that comes from the spring K and the force that comes from the dashpot. Exactly like before, the force that comes from the spring depends on the elastic constant of the spring and the displacement. The force that comes from the dashpot depends on the coefficient of the dashpot, and it depends on the velocity of the object. So we can write like Fc, which is, let's say, the force from the dashpot, as product between c, which is the constant, and x dot of t. So c is the damping coefficient, and the units of the damping coefficient are Newton per second over meters, or kilograms over second. Even in this case, by looking at the forces applied on our body, we can start from the Newton principle, summation of forces equal to mass time acceleration. If we look at all these terms, the equation of motion in this case looks like this. We have m x double dot plus c x dot plus kx equal to 0. In this case we did a little bit of manipulation of this equation, because if you remember we introduced the concept of critical damping and damping ratio. So the critical damping was introduced as 2m omega n. It can be written also in slightly different ways. It can be written also as 2m and then square root of k over m, or 2 and then square root of k times m. These three forms of the critical damping are equivalent, of course. We also introduced the concept of damping ratio. The damping ratio is indicated with the letter zeta, and is indicated as a ratio between the damping coefficient and the critical damping. So it will be C divided by C critical. And from the definition of C critical, we can write this as C over 2m omega n, or C over 2 square root of km. Once we introduce again this concept of the damping ratio, we can actually rewrite the equation of motion, and the equation of motion becomes in the standard form as x double dot plus 2 times zeta omega n x dot plus omega n square x equal to 0. Any questions so far? So at this point, if you remember, we said that okay, this is the particular form, excuse me, this is the standard form of the equation of motion. We can have three different cases. So the three different cases depend on what we have for zeta. So we can have three different cases because zeta, which is always positive, can be, actually we have four cases. We can have zeta equal to 0, we can have zeta between 0 and 1, and then we can have zeta equal to 1, or we can have zeta greater than 1. So we can try to do a little schematic of what's going on in these different cases. So let's say here. So this is zeta. If zeta is equal to 0, what kind of system do we have? We have an undamped system. So if zeta is equal to 0 from this equation here, of course all this term becomes 0, which means that we go back to the previous situation where we have x double dot plus omega n x equal to 0. So when, which is the situation of undamped system. So here we can put, again, when zeta is equal to 0, undamped. Then we have the second condition when zeta is between 0 and 1, so if this is 1, so we have all this range here. What happened in this case? In this case we have what is called an underdamped system. Then we have the third case, where zeta is equal to 1. In this case we talk about a critically damped system. And then we have the fourth situation, where zeta is greater than 1, so from here on, theoretically zeta can go to infinity. So in this case we talk about overdamped system. So basically here we have that zeta, basically when we have, in this case zeta basically tells us how the system behaves. And in particular we can also make another distinction, because this value of zeta tells us if the motion is oscillatory or if it is non-oscillatory. So if zeta is lower than 1, the motion is oscillatory motion. If zeta is, so let's say zeta lower than 1, which means between 0, including 0 and 1. If we have zeta that is greater or equal to 1, the motion is non-oscillatory. Yes. That is well, zeta is a real number. It's not an imaginary number. So because zeta comes from C, K and M. So this is always a real number, and again it can be lower than 1, it can be from 0 to infinite, and then when we look at the different values, it can be undamped, underdamped, critically damped and overdamped. But zeta is a real number. Okay. Other questions? So last time, actually, when we introduced this one, we looked only at the case of underdamped system. Now actually I think it's a good equation to see how the other solutions look like. Again, it will be a matter of seeing what kind of solution we have. So just to recall the case that we saw before, so when we have underdamped motion, again when zeta is between 0 and 1, we have that the solution x of t looks like a e to the power of negative zeta omega n t multiplied by sine of omega dt plus phi. Now here we can see that there is like a new parameter, which is omega d, and omega d is the damped natural frequency, which is also related to the natural frequency. And the relation is the following. We have that omega d is equal to omega n multiplied by the root square of 1 minus zeta squared. So this quantity is the damped natural frequency. Which, of course, when zeta is equal to 0, becomes equal to the natural frequency, because if zeta is equal to 0, 1 minus 0 is 1, square root of 1 is 1, so omega n times 1 is equal to omega n. We can also write the expression of amplitude and phase for this case. So we have that the amplitude A is equal to V0 plus zeta omega n x0, and this is squared, plus x0 omega d, and this is also squared, and then we have divided by omega d squared, and then we have a square root for the entire expression. If we look at the phase, we have the arctangent of x0 omega d divided by v0 plus x0 zeta omega n. Of course, even in this case, if zeta is equal to 0, it means that this term becomes 0, this omega d become omega n. Here we have also omega d becomes omega n. This zeta 0, this becomes 0. So basically we go back again to the situation of undamped single degree of freedom system. We said that in this case the motion is also an oscillatory motion. So if we do, even in this case, a qualitative diagram, or a qualitative plot, I would say, this is how it looks like. So a difference between what we saw before, where we had like a constant amplitude, and what we see here is that in this case the amplitude decreases with time until the motion is completely cancelled, no motion anymore. And here I have omega n. Let me double check. I have omega n, yes. My notes. Do you have something different? I didn't check the textbook, but I think it's omega n. Okay. Okay. It's yeah. This is n. This is d, and this is d. Okay. So again, this function that we see here, this plot of x as a function of t, of course is the combination of two functions. One is the sine wave, that's why we have the oscillation. The other one is the exponential. So basically this term here, the exponential, will tell us how quickly, the function, the oscillation will go to 0. So we can think about this like a sine wave that is constrained between, two exponential functions to reduce the amplitude. And this is still an oscillatory motion because we have that the mass in this case crosses the 0 position multiple times. Again, we didn't talk before about the other two cases when we have overdamped motion and critically damped motion. We can quickly look at them now, at least at the equations, because again, this is not like from a vibrational point of view, is not something we are interested in because they're both non-oscillatory motions. But I think now again it's a good equation to look at least the equations. So the second case, which is the critically damped motion, so when zeta is equal to 1, again we have critically damped. In this case the solution has the following form: a1 plus a2t times e to the power of negative omega n t, and then we have that a1 is going to be equal to x0. Of course, even in this case the two constants depend on the initial conditions, so a1 will be equal to x0 and a2 will be equal to v0, initial velocity, plus omega n x0. And then the third case, when we have overdamped motion, so zeta greater than 1 in this case, the solution looks a little bit more complex because we have that x of t is going to be equal to e to the power of negative zeta omega n t, and then this multiplies the following function. So we have a1 e to the power of negative omega n, and then square root of zeta squared minus 1 times t, plus a2, and then we have the same basically to have here without the negative sign. So it is e to the power of omega n square root of zeta squared minus 1 times t. Even in this case, of course, we have to find the expression of a1 and a2 based on the initial conditions. So what we have is a1 equal to negative v0 plus minus zeta plus square root of zeta squared minus 1, and this multiplies omega n x0, and then the denominator will be 2 omega n and then square root of zeta squared minus 1. This is for a1. If we look at a2, we also have v0 plus zeta plus square root of zeta squared minus 1 that multiplies omega n x0. The denominator will be the same because we have 2 omega n square root of zeta squared minus 1. Again, in these two cases, critically damped and over damped motion, we don't have oscillations. That's why the motion is called non-oscillatory. Make sense? Any question? Alright, after looking at the force method, we also looked at the energy method to find the equation of motion. So let's review a little bit about the energy method. So the energy method is based on the principle of conservation of energy. Of course, the principle of conservation of energy can be used only when we have conservative forces, which means that, for example, if we have friction, let's say between a block and a surface, this principle is not applicable anymore. Or, for example, if we consider let's say an object that is moving in air, and we look at the friction drag between the body and air, in that case we cannot apply anymore. But we can still apply this in many different situations. So the principle of conservation of energy basically tells us that the energy content of a certain system doesn't change in time. So when we look at two forms of mechanical energy, we can look at kinetic energy and potential energy. So in mathematical form, this principle can be written as follows: simply T plus U equal to constant. Again, the total mechanical energy, which is a summation of kinetic and potential energy, remains constant in time. Now, in the system that we typically find, we have two forms of kinetic energy and two forms of potential energy. The two forms of kinetic energy are translational kinetic energy and rotational kinetic energy. So we have T, again, two forms. One is translational and the other one is, as we said, rotational. From a physical point of view, they are identical. It's just that one refers to a linear motion of a certain object, the translational one, and the other one refers to the rotating motion of a certain object. Of course, both are related to the velocity of the object. In this case, we look at the linear velocity, so we can write the t, let's say sub t, to mean like translational kinetic energy, would be equal to 1 over 2 multiplied by the mass and then multiplied by the velocity squared. We always want to write this one in terms of our coordinate. So in this case, typically the coordinate is a linear coordinate, in this case, so x, so we can write this as 1 over 2 mx dot squared. For the rotational kinetic energy, we can use sub r, so we have 1 over 2. We still need one term related to the inertia of the object. The rotational inertia will be the moment of inertia, so we have I, and then omega square, where omega in this case indicates the angular velocity. Even in this case, we want to indicate the angular velocity with respect to our variable, so we can write this as 1 over 2 I theta dot squared. This is for the kinetic energy. We said that we also have potential energy that we typically indicate with letter U or letter P or letter P sometimes. So even in this case we have two forms of potential energy. One would be the gravitational potential energy. The other one will be the elastic potential energy. So the gravitational potential energy is related to the height of a certain object with respect to a certain reference point. It is also related to the mass of the object and the acceleration of gravity. So we can write the gravitational potential energy as mgh. The elastic potential energy, on the other hand, depends on the elastic constant of the spring, and it also depends on how much we are either stretching or compressing the spring. So in general, we can indicate this as 1 over 2 kx. So once we look at our system and we look at the energy content of the system, so we look at all the forms of potential and kinetic energy, we can finally put them together, and then from the principle of conservation of energy, if the summation is constant, it means that the derivative of the summation must be equal to 0. So we have d in dt of t plus u must be equal to 0. And when we calculate this derivative, please pay attention, this is derivative with respect to time of our variables. Here, to simplify, for example, we write x dot squared, but we know that this is x as a function of time squared. Also theta, same thing, is theta is already itself a function of time. So when we derive, we have to consider the chain rule to calculate like the full derivative. So when we apply this, condition here. So we plug the expression of kinetic energy and potential energy, we derive, and then typically we need to do some simplification, and then we finally obtain the expression of the equation of motion, from which we can calculate, of course, the natural frequency. We can also use the principle of conservation in a slightly different way, of conservation of energy in a slightly different way, because we can use as T max equal to U max. If you remember a couple of lectures ago, we worked through this one to obtain this expression here. So if the summation of potential and kinetic energy is constant throughout the time, it means that these two, the relative quantity can change, of course, but the summation is total. So if the relative quantity can change, it means that we may have situations in which we have only kinetic energy, which in this case will be the maximum kinetic energy we can have, but we can have also situations in which we have only potential energy, in which case means that we have the maximum potential energy. So these two must be equal to each other, so that's why we came up with this T max equal to U max. We know also from previous lectures that the maximum kinetic energy is related to the maximum velocity that the system can reach. The maximum velocity we indicate with x dot max. The maximum velocity is related to omega n times a, the amplitude of deflection. On the other hand, when we look at U max, maximum potential energy is related to the maximum displacement, and we know that the maximum displacement is nothing but the amplitude of the wave, so a. When we also in this case we find the kinetic energy and potential energy, if we plug here, we can actually find directly the natural frequency of the system. Also, this is very interesting. For example, if we look at the oscillatory motion, let's say, of a mass connected to a spring, we can see that when the spring is stretched to the maximum, it means that we have the maximum potential energy, which is basically when the mass stops the motion, because it is like at the maximum extension of the spring, which means in that situation, if the mass stops for an instant of time, it means in that instant of time the kinetic energy must be zero. On the other hand, the maximum velocity that we can obtain will be at the situation where we have equilibrium, so when we have static equilibrium, which means when the spring is not stretched or compressed. So if we look at the example that we were seeing before, where we have, let's say, a mass connected to a spring, like in this case, if this is the, let's say, static equilibrium position, which is where the spring is not stretched or compressed, when we actually have motion back and forth, on one side we will have maximum stretch of the spring, which means maximum potential energy, but this is where the mass stops, so it means that we have zero kinetic energy. Same thing occurs on the other side. When the spring is compressed, is completely compressed, it means that we have also the maximum potential energy, but which means we have zero kinetic energy, because basically the mass stops and then restart on the other side, restart the motion on the other side. On the other hand, when we are in the middle, we have again maximum kinetic energy because we have zero potential energy, because in this case the spring is not stretched or compressed. So again, the summation of these two quantities is always the same, but to a situation where one is zero, the other one is max, and vice versa. Make sense? Yeah. Yes. This is squared. Thank you. Any other question or comment? Alright, we touched a couple more topics so far. We talked about equivalent springs also. So equivalent springs, we started by looking at springs in series and in parallel. Remember that the condition for having springs in series is that they are subject to the same force. The condition for having springs in parallel, it means that they are subjected to the same displacement. In both cases, we found the expression of the equivalent stiffness. So when we look at springs in series, the equivalent spring, the equivalent constant is equal to 1 over summation of 1 over ki. Again, this is valid for as many springs as we want. When we have parallel springs, the K equivalent would be equal to summation of Ki. We also looked at equivalent springs from a different point of view, because we said that materials that are elastic, or in general materials that are linear elastic, also behave like springs, depending on what type of motion we have for example, let's say a beam. And then in this case we also listed 4 examples. The first example is when we have longitudinal motion. When we have longitudinal motion, we can also come up with an equivalent stiffness, which is given by EA over L. We can also have a transverse motion. In this case, the K equivalent will be equal to 3 EI over L cubed. And we also have the torsional motion. In this case, the K equivalent is equal to J over L. These two are the same. This is the elastic modulus of the material, of the beam. Here A and I are respectively the cross-section, the area of the cross-section. I is the moment of inertia of the cross-section. And then we have that L is the length of the beam. When we look at the torsional, here we have that G is the shear modulus of elasticity, and J is the polar moment of inertia, and L is the length, exactly like in the other two cases. The last topic that we looked at is the logarithmic decrement. that we indicate with the letter delta. And if you remember, the logarithmic decrement is something that we use to determine the properties of a certain material, of a certain vibrating system, starting from the response. So far we saw the response starting from the properties, but we can also do, the other way around. We can look at the response, and from the response we can determine the properties. So we have we start from the definition of logarithmic decrement, which is the natural logarithm of the ratio between the displacement at a certain time and the displacement at a period after that time. So we have x of t divided by x of lowercase t plus uppercase t. We know that for undamped systems we can write this expression. We have the delta is equal to zeta omega n t. If you remember, we went through a few steps, so you can go back to the notes and look at how we obtain this from this. And then we can also, once we have this, we can relate, obtain the value of the period, and what we obtain is the following. We have that delta is equal to zeta 2 pi divided by square root of 1 minus zeta square. As we said before, our goal is to find the properties of the vibrating system from the response, which means that we have to rearrange this expression here. So we have that zeta is equal to delta divided by square root of 4 pi square plus delta square. Which means that if we have a vibrating system, again this is valid for underdamped, we know that the plot, the qualitative plot of an underdamped system would look, let's say, like this. So this is time, this is amplitude. Basically what we need to do, we need to look at the amplitude at a certain instant, and then the amplitude after one period. And then basically what we do, we can plug this quantity here, this quantity here, so we can calculate delta, and then we can, once we calculate delta, we can plug here and here, and then we can find the damping coefficient, damping ratio. This is the damping ratio. Makes sense? And this is a summary of what we have been doing so far. We also talked last time actually a little bit about stability, but I'm not going to include that in the midterm. And so again, my suggestion is to go back to your notes, problems. Now you also have the recording of not all the lectures, but for most of them at this point. So you can go back, and if you need, you can look at those again as well. Alright, we have a couple of minutes. Do we have questions? Yeah. Yes. Yeah. Unless it is specifically required to derive a certain equation, but otherwise you can just use the equation without deriving it. Other questions? After this, we will start to talk about forced systems, and then after forced systems, we will talk about multiple degree of freedom. Yeah, no, not yet, not yet. This E term is the Young's modulus, yes. This one and this one. This one is the shear modulus of elasticity. Other questions? So if there are no other questions, we will again, we're not going to meet next Monday, but you will see again the exam available Monday evening at 7:30, and it will be available until 8:50, so 1 hour and 20 minutes. If you have questions between now and Monday, don't hesitate to send me an email. I will try to reply as soon as I can. Alright. No, no, it's a take home, so yeah, no Zoom next Monday. Alright? Alright. Have a good night, everybody, and see you in 1 week. Bye. Edwin, you can go to have dinner now. Cool. Yeah, I need to tell them actually now. No, I'm not. Yeah, oh, they are upstairs, and yeah, I need to tell them to be a little more quiet during this time. uh, bye, bye, see you, bye. Bye.